Imagine Earth's atmosphere suddenly containing twice as much oxygen as today. Our air would change from about 21% oxygen to roughly 42%. That single physical change, a doubled oxygen fraction, would ripple quickly through chemistry, biology, climate, and human systems. In this episode, we'll walk through the physics and biology, the immediate hazards, and the surprising second-order effects. Larger insects and easier fires, altered plant physiology, shifts in microbial decomposition and carbon cycling, and measurable impacts on human health and infrastructure. Start with the basics. Oxygen is reactive. At higher concentrations, oxidations proceed faster. Materials that are normally stable in ambient air become more flammable. Sparks that once went out will start combustion, and small smoldering fires can suddenly burst into flames. Practical consequence 1. Wildfire risk would rise dramatically in dry landscapes. Fire seasons would lengthen, and suppression would become riskier and costlier. Combustion engineering, from building codes to vehicle design, would need rapid overhaul to avoid catastrophic structural and transport fires. Next, consider animals. Modern arthropods and insects breathe with tracheal systems that deliver air directly to tissues. In Earth's distant past, when atmospheric oxygen was higher, we saw giant insects. Dragonflies with meter-wide wings, and millipedes the size of small dogs. A rise to about 40% oxygen is not exactly Paleozoic levels, but it moves us well toward conditions that support larger body sizes in small animals. Insects would likely grow larger, develop faster, and survive in greater numbers. Agricultural pests could explode in abundance, changing crop protection and food security. Mosquito populations might increase in size and metabolic rate, potentially altering disease dynamics. What about humans and other vertebrates? Human physiology is tuned to 21% oxygen at sea level. Breathing air with 42% oxygen increases the partial pressure of oxygen we inhale. Short-term exposures in normal pressure would usually not cause immediate seizures like hyperbaric diving incidents do, but increased oxygen availability raises cellular production of reactive oxygen species. Over time, that escalates oxidative stress, damages lipids, proteins, and DNA, and accelerates inflammatory processes. Chronic hyperoxia can injure the lungs, a recognized medical condition known as pulmonary oxygen toxicity, and may increase rates of respiratory inflammation. People with certain vulnerabilities, children, the elderly, or those with cardiovascular or pulmonary disease, would face higher acute risks, especially in enclosed or poorly ventilated indoor spaces, where local oxygen concentration could become even higher. Another human-scale hazard is oxygen enrichment in enclosed spaces. Industrial workplaces, hospitals, or even homes using oxygen-rich atmospheres for exotic industrial processes would become far more dangerous for routine tasks that produce sparks. Small electrical arcs, static discharges, or overheated bearings could more easily ignite fabrics, insulation, or lubricants. Aviation safety would change too. Jet fuel ignition chemistry and engine behavior would require re-evaluation. Fires in confined cabins would spread faster and be harder to extinguish. Plants respond to oxygen differently than animals. Photosynthesis depends on CO2 more than on O2, but oxygen matters because it competes at the active site of rubisco, the enzyme that fixes carbon in C3 plants. Elevated oxygen relative to carbon dioxide increases photorespiration, a wasteful side reaction, and reduces net carbon assimilation in many staple crops like wheat and rice. That means plant growth would not automatically accelerate. In fact, yields for C3 crops could decline unless CO2 were proportionally higher, or plants had C4 physiology or engineering to compensate. Some species might grow faster because of increased respiration-driven nutrient cycling, while others would be stressed by higher oxidative damage or photorespiration. Overall, agricultural planning would need to shift toward crop varieties and farming practices resilient to higher O2 ratios. Microbial and decomposition dynamics would also change. Aerobic microbes breathe oxygen. Higher O2 would speed aerobic decomposition of organic matter, accelerating nutrient release and CO2 emissions from soils and dead biomass. Faster decomposition means shorter carbon residence times on land, a potential positive feedback for atmospheric CO2 and climate. At the same time, some anaerobic processes, such as methane production in wetlands, would be suppressed by higher oxygen intrusion, possibly reducing methane emissions locally. The net greenhouse gas effect would be regionally variable and complex. Atmospheric chemistry and the ozone layer would not remain static. A higher oxygen concentration alters rates of photochemical reactions. In the stratosphere, more molecular oxygen could increase the raw material for ozone formation under ultraviolet light, but chemical balances also depend on catalytic cycles, driven by nitrogen and chlorine species. Surface chemistry could lead to higher production of certain oxidants, like ozone or other reactive oxygen intermediates, at ground level in polluted urban air, worsening respiratory irritation. Predicting exact changes requires detailed atmospheric modeling, but we can say with confidence the chemical regime would shift, and air quality management would face new challenges. A doubling of oxygen also affects materials and corrosion. Metals and organic polymers oxidize faster. Infrastructure lifetimes for things like bridges, pipelines, and electrical systems would shorten unless materials and protective coatings are redesigned. Paints and lubricants that were stable in 21% oxygen might oxidize, embrittle, or catch fire more readily. This creates a large engineering and economic burden to retrofit or rebuild assets for a higher oxygen world. There are intriguing ecological and evolutionary consequences. Increased oxygen availability could favor aerobic predators and highly active animals while stressing low-oxygen specialists. In freshwater systems, higher atmospheric oxygen could increase dissolved oxygen concentrations, benefiting many fish species. But if increased combustion and nutrient cycling lead to eutrophication, local hypoxic events could still occur. For long-lived species and ecosystems, evolutionary shifts over centuries or millennia would favor traits that tolerate oxidative stress, exploit higher metabolic power, or avoid new fire regimes. If the change were abrupt, within a few generations, we would expect significant mortality across sensitive taxa and major ecosystem reorganization. On human society, the immediate priorities would be fire control, medical response, and agriculture. Wildfire suppression capacity would need to expand dramatically. Building fire codes would harden. Hospitals would prepare for increased respiratory ailments and oxidative injuries. Food security strategies would prioritize crop varieties less affected by photorespiration, such as C4 crops, and invest in protective storage against larger pest outbreaks. Energy and transport systems would invest heavily in non-flammable materials and redundant safety systems. Could humans mitigate the risks? Some adaptations are feasible: engineering safer materials, redesigning ventilation and fire detection systems, shifting agricultural portfolios, and deploying targeted public health responses. But many changes are costly, and some processes, like faster soil carbon turnover or altered atmospheric chemistry, would be hard to offset. At planetary scale, a doubled oxygen fraction changes the boundary conditions for life and industry simultaneously. Mitigation would be an enormous multi-decade, multi-sector task. What about the upside? Certain processes speed up. Aerobic metabolism can support higher activity in some animals. Faster decomposition returns nutrients more quickly to soils in managed systems. Some industrial combustion processes could be more efficient, but those localized benefits are overshadowed by the systemic hazards of more frequent fires, higher oxidative stress on living organisms, and large material and infrastructure vulnerabilities. Finally, the thought experiment underscores a broader lesson. Atmospheric composition is not a neutral backdrop. Small changes in the relative abundance of a reactive gas like oxygen rewire chemistry, ecology, and technology. Earth's current oxygen level is a balance struck by photosynthesis, burial of organic carbon, and planetary geochemistry over deep time. Doubling oxygen would be a planetary reset, physically possible only via massive long-term changes in global biogeochemical fluxes, and its consequences would be profound, uneven, and expensive to adapt to. If this exploration sparked your curiosity, follow for more. What if facts that track a single physical twist to its global impacts? Follow for more. What if facts?